Yes.
Okay, perfect. So our last speaker for this session is Andrew, and he's going to talk to us about ABIs and how binaries talk together, I guess.
Yeah. Hi, everyone. My name is Andrew. I'm going to talk to you a little bit about application binary interfaces, ABIs. Also, if it's okay with the organizers, I'm fine to take questions throughout if that works for you all. Okay, so this word ABI is kind of a scary one sometimes. I came across this article just recently by someone who works on ABIs for a living, and the words they use are three-letter demon and a contract was forged in blood, which is a little dramatic, and there's this mystique around ABIs, and I think really fundamentally the reason is that we don't have a good real definition for what an ABI is or what an ABI should be. If you try to find out, usually you get answers like what is in an ABI, like what an ABI has, but not necessarily what it is. It has to cover things like data layouts and calling conventions. We know those things. Name mangling is another one that comes up. But if you read ABI docs, they're allusions to other things that are a little bit more semantic, like safety invariants and ownership. But those don't ever really come up in the definition of what an ABI is. But I think this question is becoming more and more pressing because there are all these new systems languages who are really starting to care very deeply about what an ABI is and what an ABI should be. And I think everyone in this room at least implicitly cares about what an ABI is. And some of the problems that we love in this community really can be phrased, I think, as ABI problems. So let me give you a few examples. We've got two arbitrary BlueLang components here. They're interacting over some interface, which I'm using. They're sort of like puzzle pieces. This interface, for now, you can think of it as like a type, let's say. And we have some nice type system. I know it's okay to link them together there. But a problem that we love in this community is separate compilation, which is that it's all well and fine if our type system says that they're compatible, but after we compile, are their implementations still actually compatible? And that might not even be with the same compiler, right? We could be compiling with completely different compilers like GCC or Clang, or even different compiler versions. And if we want to make sure that we're in sort of a nice language ecosystem where people have the flexibility to compile differently, we need to ask the question about what is sort of the standard that compiled components can expect to follow to make sure that the linking works out still at the target level. And with this in mind, it doesn't even need to be the same language on both sides, right? We think a lot about interop in our group. And mostly in recent years, we've been thinking about interop at sort of this level, the source level, right? So I have my two languages here, the BlueLang and the GreenLang, and I want to put them together. And there have been all sorts of cool ideas about what sort of source level mechanisms we can introduce to interface these two languages. So multi-language boundaries is an operational approach Matthews Findler introduced back in 2007. More recently, my colleague Daniel presented this idea of linking types, which is a type level approach to bringing types from another language into your own language. But I mean, more generally, just about every language out there has a CFFI. And if you've ever had the pleasure of working with a CFFI, you know that's not necessarily the best mechanism, but it is a mechanism. We all do it. It's essential. And there's this same question, really, of after we use any of these mechanisms, whether they're sophisticated or a little bit more rudimentary, we can ask the question, how are we laying things out? Is it actually safe for them to interact after we compile? And there's one more application that I think is really important. It's a slightly different setup than the previous two, but it's really important, especially for all those systems languages that I mentioned before, which is shared libraries. Okay, so there are some libraries on your computer that just about every other application uses, and it's really important that we're able to update those libraries without forcing everyone in the world to recompile, right? Maybe that's a security patch. Okay, but after we do that, there's a really serious question of whether all those old clients that we didn't want to recompile can actually still run with the new version of your library. If you've ever found yourself in DLL hell, I think everyone has at least once. this is like an instance of that problem. And really, this can be phrased as a question of whether you broke ABI and what kind of updates you're allowed to make without, forcing all your clients to change their interface. That can be phrased as an ABI question. And so, as I mentioned before, there's a sort of growing dissatisfaction with the status quo in certain language communities, especially communities that have slogans like rewrite it in Rust. If you want to be able to sort of move forward, we have to ask ourselves whether, we're in 2024. If you want an FFI between any two languages, chances are you're going through C. Is that the best that we can do these days? And actually, if you dig around in the Rust internals, there are a lot of times where Rust's compiler is laying things out like C would lay it out, just because it's convenient and stable, and everyone knows it's not going to change. And that's kind of funny, I think. And there's, I put it up on the slide before, there's a brand new RFC for Rust to tackle some of these questions about where they should go with an ABI, whether that's even a good idea. But this is sort of uncharted territory. We don't have a lot of data points. We pretty much have C's ABI. Some compilers have internal ABIs, but they're not stable. And then we have Swift's ABI, which is pretty bold, and I'll mention some of the ways that's the case later on. But I think as a compiler community, we have a unique opportunity here to sort of influence the way that things play out. And the question that we're interested in is, can we provide some sort of semantic foundation that would lay the groundwork for making some of these big decisions? And I think in order to do that, we have to actually answer that question from earlier, like what an ABI is and not just what an ABI has. And I think really the question from my perspective is a very simple one. If I have some source interface, which is specified maybe in like a header file or something, again, you can think about it as like a type for now. What target programs does it describe? If I'm linking against this interface, right, which target programs, which components should I expect to be able to link with? Yes?
Target means an assembly. Target means an assembly language or one specific target? Or?
It really, technically, it means a platform. But we'll see in the setup in a moment what at least the Rust proposal has been so far is that instead of starting all the way from scratch, we can build on top of another ABI, which is C's. So because the C's ABI is defined on every platform already, we can reuse some of their basic ABI mechanisms, like which things will go in registers and which things will go on the stack. We can reuse that. Okay, but there are some bits we want to add on top. So for now, you can think of it as whatever your lowest common denominator is. That may or may not be assembly, depending on which way you want to go.
Right. So maybe just as a comment or a question, I don't know. So, but the way I understand this, the fact that every language uses C as an FFI is largely because that's a common denominator, and because you don't want to specify for every target independently.
Yes, and in fact, we're going to see in the concrete example, it's going to be C that we're going to build on. Yeah, because it's very convenient. I should say, we'll talk about it at the end. We have some other ideas for alternatives. I guess I could give a spoiler. WebAssembly would be another good choice, we think. Great question. Yeah. Okay. So I think this is like the intuitive role that an ABI should play. It's sort of an expansive definition, I think, but when we're talking at this level of the semantics, I think it's a useful one. And to make this ever so slightly more formal, again, for us, an interface, at least right now, will be a type, right? And really, we're just asking the question, which target programs behave like that type? Okay. And if you happen to catch Amal's keynote last year at PriSC, this may look familiar to you. She talked about realizability models and semantic typing. If you have not seen that before, I'm going to cover it again, so don't worry. But this is sort of the core idea. For now, you can just think of this as some set with a very, very fancy predicate on target programs. Okay. And then the question of ABI compliance, right? Like, am I actually following this standard linking protocol? Is, there's a lot loaded in that containment, but like, that's really the ultimate question: is, do I satisfy the model? Okay. Now, semantic typing realizability models, that's something that we've been working with for the past couple of years. But we've been using it as a proof object. It was like a means to an end. And what I just gave you was a definition. Okay, so there's this really, I think, interesting question which doesn't really have like a straightforward answer. It's a qualitative question. Is this a good spec? Like, is this a good idea? Is this the right way to talk about ABIs? And I think there are sort of two questions we need to answer in order to evaluate that. One is about the spec itself, right? So ABIs, they have to really get into the weeds, the nitty-gritty. Can you actually get low enough of a level with this kind of specification? I think we've seen a lot of promising efforts over the years to indicate that that is the case, but it still is an important question. Like, will the ABI committees buy into this idea? Will they accept this as a kind of definition that they can work with and write compilers against? And then the other one is the way that it's going to be used. Oh, yeah.
Any question that begins, will the committees accept, has the answer no.
Yes.
They have a fine bunch of APIs. They've been stable for I don't know how many decades. They're great.
Yes. No, I think that's a good point, is that, you know, there's a precedent, and the reason that, someone mentioned it before, the reason that everyone uses C's ABI is because it's there and it hasn't changed ever, and it probably won't change ever. And there's a lot of benefit in that. Had there not been any of these RFCs, had Swift not published an ABI stability manifesto, then I would not be interested in this question. It would just be C for the end of time. But I think there is sort of a growing demand to do something a little bit richer and move forward. Okay, and yeah, the second one is just, so there was the formalism itself, and then on the second aspect of that is we should be able to prove all of the examples that we saw before and potentially much more. Yes?
Yeah, just to understand, I mean, couldn't the C ABI also be specified in this way?
Absolutely.
Okay, so then it's not about changing it, it's about whether this is a good way to specify it.
Absolutely it could, yes. Okay. So to make things a little bit more concrete, we're going to look at some examples covering those 2 points, both the formalization and the applications. In this example, we'll take a sort of functional language that you'll all be familiar with, and the target, like we just mentioned a few minutes ago, will be something C-ish for now. You can keep that in mind. Even though there's no references in the source, the implementation is going to box all the values, at least for the purpose of this talk, just to sketch out some of these ideas. And the way that we're actually going to specify the ABI itself, specify this model, I said the predicate would be pretty rich. It'll actually be given as a separation logic specification. Okay. So if you have not seen semantic typing before, the key idea is that we want to characterize which dynamic terms behave like a certain type. Okay, so we're going to keep our typing judgment in mind, right? The only twist that realizability adds is that the program that we're using, the program that's running that's supposed to behave like that type, is not actually drawn from the same language as the type itself. Okay, so in this case, the question that we're asking is, when does a target program behave like a particular type? Okay, and intuitively, if using like a Hoare triple notation, right? We just want to know if we have some pre-state that sort of acts like a gamma, right? And we run that target program, then we should get back a value that behaves like a t. Okay, that's like the core idea. And like I said, at least for this example that I'm going to show you, we're going to box everything. So we're just going to take the result. The result should be boxed. It should behave like a reference to a t. Right? It should be some location that acts like a reference of a t. And everything in our context, those should also be references. So if you're like, what is this R thing? I'm punting the definition. It's going to be on the next slide. But for now, intuitively, it says if you give me a bunch of references that satisfy my context, then I should run to a value that behaves like a t. Okay? So what is this reference thing? Well, one of the things we have to do is we have to specify the layout. So all of our references are going to be laid out like this. We have the counter in the first position, and then we have some object adjacent to it. Okay. And we're going to do this for all of our types. So the references have a uniform representation. Okay. But all of our different types will have a different object representation. For example, integers, right, will have pretty much the natural representation, right? It's just going to be some integer sitting there. Okay. And we're going to do this for each of our types. I should say, if it bothers you that we're boxing integers, you could very easily modify this so that R was not necessarily a uniform representation where we're reference counting. You could use something like pointer tagging to get unboxed data, and that's something that we've been experimenting with as well. Okay, so this is one bit, is like the data layout itself, right? But the way that these references behave, we want to capture richer properties than just layout. The way that these properties behave is a key part, I think, of moving toward a richer specification. So really, each reference in this logic will come with sort of a lower bound on the count. Okay, so if I have one reference, then I know the count's at least one. And likewise, if I have 2 or 3 references, right, I learn that the lower bound on the count is higher and higher and higher, right? If you like rules, then the rule would look something like this, right? If I have a reference, I have the permission to increment that reference, okay? And I do know that the count is greater than 1 by virtue of having it in the first place. Yeah? Oh, 5 minutes, okay, yeah. And I can go in the other direction as well. Right? So if I start with 3 references, I can go down and down and down, but of course each time I have to be a little careful, right? Because when I have a reference, I don't really know, it's just a lower bound. There could be some other reference out there that I can't see. This is like your frame condition, okay? And then the count would be strictly greater than 1, and when I drop it, well, I don't know, the count's greater than 0, I don't have any of those references, and I don't keep any reference to this object whatsoever. So I get back nothing. I have no obligations, and I also have no permissions regarding that pointer, okay? The other case is when it's exactly 1. Sorry, I skipped ahead. The other case is when it's exactly 1. This really is the last one that's remaining, and in this case, right, once I decrement, I've gone all the way to 0, and importantly, I get back ownership of the underlying object. So a way that you can think of a reference is it's sort of a permission to increment and read and all of those things. But it's also an obligation to decrement. This is going to come with resources that need to be collected, right? So this might have references of its own, and those will need to be dropped for garbage collection reasons, right? So you get back permission to call the destructors sitting in O. Okay. And this shape is pretty much like the reference shape that we started with. In fact, if you set it up properly, right, and you initialize the count to 1, well, that's how you can introduce references in the first place, right? These 2 views, this is just a view shift on the same data. So we don't just care about the layout. We're specifying the whole protocol, which includes how you should be interacting with them, how you should manage the logical state in addition to the physical state. Okay. And this is going to carry all the way throughout. So that was a bit about the reference protocol. But even when we go to layout, right, if we were thinking about how we're just going to lay out pairs for now, right, if your ABI was just specifying the physical resources, you'd probably start your specification like this. Okay, we have a uniform representation, so it's just going to be 2 cells with 2 pointers in them. And you'd kind of stop there, right? That's the data. But it's more than that. The data comes with these resources, and those are essential to the protocol as well. Right? These might have their own counts. Then we're going to have their own resources that you need to manage as well. And in this case, I guess the layout is very maybe clear because we have a uniform representation and it's just a tuple. Laying them out adjacent to each other is maybe the most natural option. But if you have records and variants, you really have to think carefully about how you're going to order the fields and things like that. Because whether you're sensitive to the ordering of the fields, whether you're able to add new fields, these are all things that are going to come up in this very definition. Okay. The other thing that an ABI is supposed to do, in addition to specifying layout, is calling conventions. So like, I mean, fundamentally as a piece of data, a function is just going to be a function pointer. But again, we're going to specify more than just the representation. We're going to specify the calling convention here, right? So here this says it's a pointer to some function pointer, but we want to know what happens when we call that function, given something that follows the protocol. So in this case, the calling convention stipulates that when we call this function with a reference of input type, it's going to consume that reference and give you back a reference of output type, right? But importantly, it's consuming it, it's not giving it back. There's another totally viable option that's used sometimes in reference counting schemes, right? Which is that you have to give back the reference. And if this is sort of analogous to like caller save versus callee save. In this case, the former is like caller retain, or caller increment if you like, right? Whereas here, right, the callee is going to have to increment if they're going to do anything interesting with it. And this is just with sort of bare functions. If you had closures, right, closures would even need to consider more. They would need to account for how the environment is passed in the closing convention, the calling convention, and there's a lot of subtlety that you can express just at this level. Okay. So that was just a taste of some of the aspects of the formalization or a potential formalization. When it comes to applications, when it comes to using the formalization itself, this was one setup that we were interested in the beginning, right? Whether we can link code from different compilers. Well, if we show that they are both compliant, which is to say they only produce compliant components, right? Then we sort of get, in the way we usually do, compositionality from the semantic typing, right? We can put them together because their semantic types are compatible, right? And just as I mentioned earlier, this isn't limited to code from the same compiler, right? It can be code from, code from the same compilers for the same language. It could be compilers for completely different languages, although most likely you'll want to show something additional here, right? About the relationship between the FFI code and the code sitting in that other language, right? Showing that actually there's some relationship between the types on the other side and the types in that green language. I would love to talk more about that if folks want. And then in this last one, the library compatibility. Really, you can think of library compatibility as sort of like a semantic subset. Right, so before it satisfied some ABI, and it needs to continue to satisfy the same ABI, which means it's compliant at the same type that it was before. And if you're thinking, well, when can I, like, what kind of changes here are interesting? What kind of changes are allowed? Swift has done some very interesting, made some very interesting decisions in its ABI. And it sort of allows a lot of flexibility in the kinds of changes you're allowed to make across libraries by default. So for example, like adding fields to a struct, adding cases to an enum. Things that like we get from nice type systems, but the ABI hasn't really kept pace. And people who are writing shared libraries in C are already doing this kind of thing. They're just doing it by hand. If you go and you look at the way some of the sort of long-lasting shared libraries are written, they'll be written with all these extra fields at the end, with null pointers most of the time, and if they ever want to add the fields, right, they'll add another layer of abstraction on, right, and they're doing this thing by hand. Whereas Swift said we want to give library authors that support by default from the language. So there's a trade-off space there. Obviously, Swift has to resolve some things more dynamically, but it's an interesting space to explore, and with a setup like this, you can actually analyze those kinds of decisions. So we're working on this case study now with a bunch of variations, some of which I alluded to throughout the talk. And I mentioned some of the idiosyncrasies of Swift's ABI that we're trying to look at. They call these resilient type layouts that are sort of accepting of certain changes to the type definitions. And they do some interesting things with polymorphism as well, because they care about code sizes. Monomorphization is not an option for them. So they have to do some interesting things to move representations. And something else we're thinking about, we're working on, is an ABI for Rust. Again, this is an active area of discussion within the Rust dev team. And we're looking at potentially doing this over WASM instead of C, specifically using the component model, which we think is, they're sort of like building blocks, we think, that you could use to construct layers of ABI abstraction, right? So you're right that you don't want to start from scratch every time. And this might provide the right sort of vocabulary for doing that thing and making it easier for languages to specify their own ABI without starting from the bottom. Okay, so that's it for me. This is sort of the pipeline that we're analyzing now. And I'd love to hear your thoughts on this. So I'll be around. Reach out to me if you have questions or you want to talk. Thank you.
So we are ready at questions, but feel free to ask.
So some of your ABI specifications seemed a lot like correctness conditions, like Hoare triples and whatnot.
Yep.
Can you say more about like how you would write those and how you would relate them to like C has a notion of what a pointer is, and that's not the same as the notion of a pointer the level of assembly. So do you have an idea of how those would be connected?
Yeah, so I think there are sort of two questions in there. So at this level, we're mostly thinking about safety, and so not fully functional correctness, although that's probably something you'd want to show, at least for the compiler example. It's not necessarily the ABI's responsibility, though. When it comes to I think you're saying the gap between the memory model of C and the memory model of the underlying architecture. That's a really great question. And I think ultimately, if this seems like a good idea, then it would be nice to also show C's ABI in this way. Of course, that would be per platform. But for now, we're just imagining this as the lowest level that you're going to go between. So like I mentioned before, Rust's team is looking to inherit the interpretation, at least for now, inherit the interpretation of pointers from C, at least at the level of its ABI. Whether that's the right decision, I don't know. But for now, they're just sort of taking it at face value, it seems. Yeah.
Okay, thank you.
One more, yeah.
So it's an interesting idea to use WASM instead of C for as a sort of common denominator. I guess one advantage might be that you have a sort of security spec for WASM, which you generally don't really have for C. So
yes.
Is that part of the goal?
I think that's part of the goal. Mostly, I mean, we're really interested in. One of the applications here is interop, and that's one that we're really interested in. But yeah, for security reasons as well, I think it's a very interesting application. And also, I mean, we'll see where the component model goes, but I really think at least the motivation there. It sounds like they're sort of establishing a vocabulary for building up ABIs that not only can you specify, but you can also type check them, which is a very, none of this was about type checking, but theoretically, if you could type check compliance, that would be, well, that would be amazing. So that might provide some sort of path to that. Right now, if you were to do this targeting C's ABI, that would just be too hard to type check at this stage. Yeah.
Can I ask another question? So one thing that does strike me as weird is that your ABI doesn't seem to specify how. It just says what are the possible legal values, not how does one source value correspond to one target value, which.
So that would be something that you'd want to show specifically for compiler compliance, right? You're probably not just interested in the compiler being compliant, but also that it's correct.
If I think about an ABI intuitively, then I think about how is a Boolean represented, not just what are the legal values that represent some Boolean.
So you're saying it should be more of a, how is a particular Boolean represented?
Yeah, I mean, if I think intuitively about an ABI, that's part of it for me.
Okay, that's an interesting idea, yeah.
If I can also add another question. So maybe the bit that I'm missing is how does this, like, your model of an ABI actually I mean, like, different languages have different assumptions on, I don't know, like, on how, wait, let me rephrase it. So, okay, here's an example. I'm thinking about, like, C code interacting with Rust code. They have different approaches to memory management.
Yes.
And here you're like thinking, okay, we put everything in a box and everything is reference counted, but
Yes.
that's not like how people that develop, like C Rust applications work. Like they, on some, if the object is like a Rust object, then is, like reference counted. If it's from C side, then if it's coming from C, then it's just a pointer to a buffer. And so what I'm wondering, like, and I'm thinking, like, whether you have ideas on how to, like, capture that. Is this more, like, subtle, maybe patterns? How could they, like, how could you make this explicit in your model? How could you guarantee that they work together?
Yeah, that's a great question. So to be clear, the boxing that's not a fundamental to the approach. That's just for this particular case study. So for Rust, you would not do that. You would do something different, where you'd model sort of their ownership, their notion of ownership, and it wouldn't necessarily be reference counting throughout, right? But this notion of, like, moving between C and Rust, right? That's something that's very tricky, but people are already doing that. All of these things people are already doing, and we just want to give some sort of handle to make some handle on that you can formalize what they're doing, and then hopefully eventually verify that they're doing it correctly, right? So, like, there are these FFI guidelines for interactions between Rust and C, okay, and it's a nice list, but we don't know if it's correct, if it's exhaustive, right? Like, it's a good sort of baseline, but this would potentially let you say, right, that if you follow these guidelines, right, then your migration from one ABI to another is correct or sound. Yes.
Last one.
I mean, like, true, like that. I mean, whether they're correct or not, I think it's not something that current ABIs really talk about. Like, what ABIs nowadays are about is just, okay, you pass a pointer, you pass an integer, and that's about it. And then, like, how you treat them, so the rest of the application has to, like, and maybe this is why this is challenging, has to know what's on the other side.
Yes.
To use them correctly.
Yes.
So, yeah, I guess maybe. So it's maybe, ideal, I guess, an ABI should, like, an ABI spec should include this type of information, maybe.
That way you know at least what the endpoints are, right? So you know how you have to move between them. That's the goal, yeah.
Cool, great.
Thank you.
Okay, maybe. Yeah. I mean, it's coffee time almost, but
Yeah, sorry, just a quick comment. So one
Yes.
thing that struck me as missing is a story for a language like Haskell, where you can, when you use an FFI in Haskell, you can say this C function is actually a pure function, so I'm gonna not run it in the IO monad, or I am gonna model it in the IO monad, or
Yes. If you go here and you look at linking types, right? That's what I was saying before. There are different source level mechanisms for interacting across languages that are really, really important. Of course, in that scenario, you don't actually know. Like, you can mark something as IO and it might not really be IO. So that's still an issue. It's still a risk. But the types that you assign to foreign code, yeah, that's a very interesting issue, and it is something we've thought about, but not explicitly as part of the ABI, but as part of, like, a compiler extension that lets you write the same way that you do foreign import in Haskell. Yeah, I would say that's more of a compiler issue than an ABI issue in its own right, but you can use the ABI to make sure that the type you're ascribing is coherent. Right, once you've imported, the fact that it's extern doesn't stick with the type. I wouldn't say it's part of the type. I'd love to talk more about it. Yeah.
So let's thank Andrew again and coffee.